Hello everyone and welcome back to the 8-Bit Guy. I have a very special demo for you today. This is something I've been thinking about for over 10 years and I finally decided to try it out and see if it works, and well, here we go. I have a simple Commodore 128. This machine has not been modified in any way. It is as stock as a stock system can be. I haven't even done the 64K video RAM upgrade in it that is very common on these machines. So this is literally how it comes from the factory. And as you can see, there's really nothing plugged into the back of this machine other than the standard things, like I'm using an SD to IEC for a disk drive. I've got a video output and the 80 column output, and of course power over here. That's all that's connected. Okay, so you're probably wondering, how does this work? And you're probably thinking, oh, well, you know what? I'm just taking the same video signal and splitting it to 5 different monitors. And I could forgive you for thinking that because right now they are in fact all displaying the same thing. But what if I told you that I could actually display a separate image on all 5 of these monitors? Well, that's what we're going to do. And there we go, 5 unique images. I wrote a little slideshow and simple paint program that works with the 5 monitor setup. I had to draw all of these myself, so don't expect any incredible works of art here. Okay, so displaying still images is one thing, but can I animate anything? Yes, in fact, I wrote another special little program. Check it out. This program displays some high-resolution graphics while also scrolling a message across all 5 monitors. Okay, so how does it actually work? Well, if you look at a typical RGBI output, it is technically possible to convert this to monochrome NTSC by just combining the red, green, and blue signals with some resistors to create various gray levels, and then the 2 sync signals need to be combined with a little logic to create a composite sync signal. I'm oversimplifying all of this, of course, but that would just drive one monitor. So my idea was to break out each of the signal lines to its own monitor and sharing the same sync signal between them like this. And so my friend Joe Burks designed and built this little board for me that does exactly that. It connects to an RGBI video signal and then outputs 4 separate composite signals. The actual schematic looks like this. It's really not that complex, as you can see. And if you look at the 16 colors available on the C128, you could look at the palette indexes in binary instead of decimal. In fact, it's really best at this point to stop thinking about them as colors at all. Each of the 4 bits will activate one of the RGBI lines, so you really just think about it from a standpoint that each of these bits represents one of the monitors. And so the 4 RGBI signals are split between the 4 monitors, and then the last one, of course, is driven by the standard VIC2 output, and that's how we get 5 total monitors on the Commodore 128. If you're wondering how my program looks on an emulator, or if I had a proper color monitor connected to the RGBI, well, this is what you'd see. In fact, this is why I designed the program to allow me to switch the 5th monitor between any of the images for editing, because in the emulator it would be a nightmare trying to edit on the other 4. And here's what the scrolling marquee looks like. Okay, so if I boot the computer on the regular 40 column display, then you will see pretty much exactly what you expect on the 5th monitor. The other 4 are blank. Now, what if we boot up in 80 column display? And this is where it gets a little bit interesting. So you see 3 of the monitors, but not the 4th. Now, the reason for this is actually kind of surprising to me. I always assumed the startup text on the Commodore 128 was white, but it turns out it's actually light cyan. And that's why the red is not used at all, which is what would be going to this one here. So, for example, if I were to change the color to red and then start typing, you'll see it show up over here. So one big limitation I had using the Commodore 128 is that you cannot control individual pixels colors on the screen. Just like other Commodore 8-bit systems, you have to work within color cells. Now, don't get me wrong, you can control individual pixels just like I did at the bottom of the screen on the scroller, but all those pixels are the same color. They're white, and so they appear on all 4 monitors. But if I want to be able to control individual pixels to the point that I can determine whether I'm going to be using the RGB or I output, then I'm kind of stuck using the color cells, which limits me to 80 by 25 screen resolution. Incidentally, the fifth monitor is having to use combinations of 4 different block characters in order to mimic the 80-column blocks on the other 4 screens. Now, here's the thing. If you look at the VDC registers, you will see it should be possible to reduce the height of the text characters, potentially down to a single pixel, but I tried just going with 4 pixels tall, doubling the resolution I had before. Interestingly enough, it works perfectly in the emulator, as you can see. However, when I run the program on real hardware, the picture is crazy distorted, and from what I'm told, this is most likely because I have an early 128, and the VDC chip is probably broken in this regard, where later models like the 128 DCR had a newer version that would probably work fine. In fact, since the DCR model has more video RAM, I believe I could possibly create a mode that would give me 160 by 200 resolution where any pixel could be any color, which would allow me for theoretically nicer images than what I've been showing. But I no longer have one of those, so I can't demonstrate that. However, the Commodore 128 wasn't the only system that used RGBI output. In theory, this device could also work on IBM CGA. The trouble with CGA is going to be similar to the C128 in that CGA can only output 16 colors in text mode. So it wouldn't really be able to do much of any better than what I've already shown here. But what about IBM's EGA graphics? Now that raises some interesting possibilities. Granted, I won't be able to use the 350 line modes because the NTSC monitor won't sync with that, but I should be able to use the 320 by 200 or 640 by 200 mode. In fact, the later mode I'm particularly interested in. And so we'll give that a try right after our sponsor, which is me. One of the coolest new products I have is this vinyl record. It has the Commodore 64 version of the Quark soundtrack on one side. That's right, a vinyl record with actual SID music on it from Noel Aman. And on the other side, it has most of the same songs remastered by Anders Jensen using modern synthesizers, and it is truly remarkable. I also have Quarks available now on the Tandy Color computer, as well as several other platforms. YouTube doesn't even pay me a living wage anymore, so I really do heavily depend on merchandise sales as well as your support on Patreon. I would also like to take this opportunity to mention that I will be in Philadelphia in just a few days at the Too Many Games convention, and maybe I'll see some of you guys there. And now, back to our crazy experiment. So with EGA graphics running in 640 by 200 mode, I should be able to break this out to 4 monitors, and each monitor should be able to have its own unique 640 by 200 image presented in 2 colors. So I borrowed this 386 from my friend Oliver and set it up, and here we go. So we do indeed get a picture. I never thought I'd see EGA being displayed on an NTSC television, but here we are. Now, at first, I thought there was a problem because I expected to see video over here when the intro text was in all white. However, one of the things I learned is that after all these years of thinking the default color on these systems was white, it turns out it's actually light gray. And so this isn't using the intensity bit, and that's why, at least at first, my far left TV is blank. Now, this particular PC needs a new CMOS battery, so I just need to go in and enable the hard drive right quick. It's kind of weird seeing different bits of the BIOS screen appear on different monitors, depending on what color those pieces are. So now, let's run our slideshow. And there we have it, 4 unique images displayed on each of these monitors from a single EGA card. I was actually quite impressed myself at how good the images look for 2-color images, but the blurriness of these TVs actually helps to make the dither patterns look more like grayscale. This wasn't easy to get working though. I ran into some weird unexpected problems that I'll show you, but first I'll show you how I created these images. As an example, I'll start by searching for a picture of Tony Stark. Now, what I'm looking for is a picture that's not too tall or too wide, and also want something with good high contrast, and not a lot of other clutter in the picture. So I'll pick this one as I think it will convert well to 2 colors. So I'll copy that and paste it into PaintShop Pro. Now the next thing, I'll need to make this image 4:3 aspect ratio. So I'll look at the size of the image in pixels, then I'll open the calculator. I'll divide that by 3 and then multiply that by 4. That'll give me the correct width of 836. So next I'll modify the canvas size to 836 by 628. There you go. This gives a proper 4:3 aspect ratio. Next, I'll need to convert the image to my target resolution of 640 by 200 pixels. And yes, that's going to make the aspect ratio look all crazy here in the Paint program. but don't worry, it'll look correct when displayed on the target system. Now, the next thing I'll do is make a second copy of it so that I can try two different conversion techniques. So I'll take this one down to 2 colors using weighted, and the other one using non-weighted, and I'll see which one looks the best. And I'm going to go with the top one. As you can see, this is just 2 colors, black and white, no shades of gray. Now, if you want to preview how this is going to look on the televisions, what you can do is double the vertical size. That'll bring the aspect ratio back, and then increase the color depth, and then add a bit of blur to the image, as the TVs I'm using will naturally add a bit of blur. And this is how it should look. And as you can see on the final image, that's pretty much exactly how it looks. Anyway, this is all well and good for creating a single black and white image. How do we combine them together so they look like this? Well, PaintShop Pro can save the image as raw data. And in this case, you'll see each pixel is an 8-bit value represented by a 0 or a 1. And so we have 4 different files. Imagine this is the first byte in each file. We need to combine this like this into a single merged byte. And then we need to move on to byte 2 and so forth until the entire file is merged. Well, I just happen to have a little Python script here that I made, which will do exactly that and spit out a combined raw image. So then I can open that image in PaintShop Pro, and since it has no header, I have to manually tell it the size of the image. Now everything appears black at the moment because our palette looks like this, and all of our pixels are in the first 16 colors, which are very dark. So next, I'll load in a special palette and tell it to keep the indexes. And there we go. This is starting to look like the finished product. But we need to do one more thing. Notice the image is still in 256 colors. Well, I can reduce it down to 16 colors, and there we go. I now have a proper 16 color image with the 4 pictures combined in this way. And when displayed on the color splitter device, you get a very nice separation of the 4 colors. Except, it wasn't quite that easy. I ran into a few problems. First of all, I borrowed some EGA cards from a friend Oliver. Now, one of these cards was just broken, and several of them worked, but when I configured the dip switches to work on a CGA monitor, how can I explain this? Normally, if you use a CGA monitor on an EGA card, you simply will not be able to use any of the high-res modes. You know, the ones that are the 640 by 350. But you should be able to use all the rest. However, many of these EGA cards, especially the Oak technology-based ones, were infuriating because when I set the switches to CGA mode, they also blocked me from using all of the high-color EGA modes, even though there's no good reason for that. However, this Trident card seemed to work just fine the way I needed. Except then, I ran into another problem. My graphics viewer of choice has always been C-Show or CompuShow. Now, one of the reasons I love it is because when you select an image, you can get to pick exactly what video mode to view it in. And I need this one right here. This is also a bit of an obscure mode, and not a lot of software supported it. However, as you can see, the image separation didn't appear to be working quite right. It took me hours to realize the problem. I created this image here so I could see all of the colors, and even if I run it in DOSBox on my modern PC, you can see the problem. Notice there should be 2 grays here, light and dark. But C-Show displays this image with just a single gray, and one of them just becomes white. And I tried playing with the palette for hours, and it just would not display 2 separate grays. This is clearly a bug in C-Show. On the bright side, I did find that Deluxe Paint does in fact support this mode and will in fact display the image correctly with proper separation of the 2 grays. And so I'm using Deluxe Paint Gallery to showcase the final pictures on the real hardware. Oh, and of course I wanted to have 5 matching monitors for this little adventure, and I already had 3 of these Samsung TVs, so I bought another one off eBay, and Adrian Black picked up one for me in Portland and shipped it to me. The lighter was known to have a blown speaker, so I thought I'd open it up real quick and check it. The speaker actually looked fine to me, but that doesn't mean it isn't blown in some way. But it really doesn't matter, as I won't be using the sound anyway. So the one I got on eBay needed to have the yoke rotated, as some of the picture was rotated slightly clockwise, so I fixed that. And also adjusted the flybacks to try to get similar brightness levels, and then I had to spend some time in the service menus trying to get the color to match on all of these, which was harder than it looks, and I still didn't get it exactly correct. I think 4 of the monitors are pretty close, but this one here is driving me bonkers. You see in person it looks exactly like the others, but on camera for some reason it does not, and I've even tried adjusting it so that it has practically a red hue in person, but still appears bluish on my camera. My only hypothesis is that for some reason this tube has a different spectral output than the others, maybe making more light in the UV or infrared regions that the camera is picking up. I don't know. I tried shining a UV light at all of the TVs in the dark to see if they look different, but they pretty much look all the same, so beats me. Okay, so now that I've shown you how this little magic trick is done, I thought maybe I'd talk about 2 ideas I have that could take this idea to the next level. Even though I won't be able to fully explore these ideas in this video, maybe I'll do a follow-up video. If you've seen my videos on IBM's CGA composite mode, then you'll know composite mode is basically just a monochrome 640 by 200 image with a color burst signal turned on. And this causes a CRT to blur different pixel patterns into different colors. The result is roughly a 160 by 200 image with 16 colors. Both of my MS-DOS games, such as Petsky Robots and Planet X3, support this mode and look surprisingly good. So we were thinking, what if this little board that we have here were also to incorporate that color burst signal? If so, that means we could have 4 monitors displaying unique 16 color images. Now, I've tried to convert some realistic images over to this mode, but the weird palette and super low resolution make it pretty difficult to get anything that looks nice. I also tried with this picture, similar result. Now, granted, I could apply a little bit of blur here, which will simulate how it would appear on a CRT, and maybe it isn't so bad, but I did find that if I used more cartoon images and cleaned them up by hand, I could get something that looks pretty good, like Homer Simpson here. Likewise, I could apply some blur, and that also helps this image a little bit. So yeah, in theory, I could display 4 different color images from a single EGA system with this method. So besides the Commodore 128 and IBM CGA EGA systems, what other systems might work? Well, one that comes to mind obviously is the Apple II, if you have an RGB card installed, or better yet, the Laser 128, since it has RGB mode built right in. But what about systems that used an analog RGB connection like the Amiga or IBM VGA systems? These systems could also work, but with some pros and cons. With VGA, you'd be able to get 3 monitors by splitting the red, green, and blue signals. But on the bright side, each monitor would have a full grayscale rather than being black and white. So as a comparison of how Tony Stark looked in my setup versus how it would look with VGA, so that's quite an improvement. Now, while this setup could certainly work with composite video, you'd have to set the VGA card to operate at 15.75 kilohertz, which can be done, and I've actually shown that before in one of my previous videos. However, if you wanted to make life easier on yourself, then you could go this route where you'd just be splitting to 3 VGA monitors and simply combining the signals for RGB at the destination so you get grayscale on each monitor. You'd also end up with a lot sharper image. It should also be pointed out that there were a number of small grayscale VGA monitors produced, typically for things like cash registers and other industrial equipment where color wasn't needed. They were also typically very small, but yeah, you could use those as well. Now, one really cool possibility with doing this with VGA would be the idea of writing a Windows video driver that specifically took advantage of this and treated it like 3 displays. Multi-monitor support was introduced as early as Windows 98, so even an early Pentium-based laptop like this one would have been able to run 3 separate monitors without much of any additional hardware. However, writing such a driver is far beyond my skill level, so I will have to leave that to somebody else. However, if somebody else does want to write one, I will be happy to do a follow-up video and demonstrate that. But that's all I've got for now, so as always, thanks for watching.